Hi and welcome to the next talk at Meeting C++ 2025. This time it will be Command Line C++ by Mathew Benson. Looking forward to your talk, Mathew. Please take it away.
Thank you very much, Jens. Welcome to my talk. The talk is entitled Command Line C++. I'll start by talking a bit about myself. My name is Mathew Benson. I am an independent C++ contractor, but I do contract on other languages and other computer-related things. I like C++ very much. I find it a very powerful language, and I like what it empowers me to do. I also like the command line a lot. Something I've grown to learn, and that's something I want to share about why I think it's a very important thing to consider learning and consider knowing about, even in 2025, though it's a very old technology. As an aside to this, something related to this, I'm also very passionate about energy efficient computing, making the most out of whatever hardware, particularly older hardware, extending its life as much as possible. So, that involves like better code, making things run as fast as possible. So here are a few of my handles online. I'll just quickly mention the last bit there, that I usually hang out at the CPP Africa Discord server. Happen to be an administrator there, but I'm not the originator of the server, but it's a place I've been contributing to and speaking at. We usually have a monthly meetup starting this year, so where we talk about C++. So generally, you're welcome to join us there. Talk about a lot more about just C++, especially in the context of developing world, Africa, and that kind of thing. So on to the talk. Generally, what I'm going to do is start with a rationale, explanation of my thought process and why I think the command line is very important. And in order to do that, I'm going to be speaking a little bit about some definitions, explaining some concepts in relation to the terminal and the command line, which may not be so obvious, especially in a world where a lot of people's first exposure to computers is through graphical interfaces. And a lot of the nuance and the certain elements of the terminal have kind of like fallen by the wayside. So I intend to kind of like dig into that a little bit, and then now go into programming in C++ with the command line, and in particular in environments where you only have the command line. I know that it is possible to access the command line even if you use, say, Visual Studio, or even Visual Studio Code is, kind of like a midway point between graphical interface and the command line interface. But the place I'm coming from is a lot deeper. So on to the first section there, the rationale, my thinking and my goals and what I think about this topic. So I do believe that C++, and of course a little bit of C, you should be aware of C, but C++ is a better language to learn in this day and age. I know there are many C developers who would argue with me about that, but I think it's good to kind of like look at both languages, though I may lean more towards C++ because of what it empowers us to do. But one of the very important things, core elements, basically, I think, in terms of with C++ is the fact that it doesn't try to overrule what came before it, but it acknowledges it even in its name. It is C. It does contain C, but it is an extension of C, and that, I think, is a very important point, especially even when you consider, say, like the command line. The command line is a very important part of our computing. And though the graphical interfaces superseded the old, terminal-based UI, it's still important to know, to be aware of it. So in the same way that when we compare C++ and C, I'm talking about comparing using the modern tools, but ensuring that from time to time to kind of like take a step back and look at where things have come from, especially in terms of the tooling. So, as many of you know, C++ is the language used to compile and to develop a lot of what we use, from our browsers to whatever Photoshop and all these applications. You generally find that they are developed in C++. There are some lower level things like the operating system, like Linux. The kernel itself is still done in C because of its nature, but it's still important to know what exactly is happening, especially like at a time like now. As we record this, I think it's October the 15th. We have the whole saga of Windows 10 being end of life, and it's bringing up this question of who's. There's a resistance to move to Windows 11 because of the whole issue of the Microsoft account, and there's the general feeling of whose computer is my computer. Does it belong to Microsoft, or is it my computer? Why can't I make decisions concerning my computer? And this also comes down to knowing, having knowledge of how your computer works gives you a certain sense of power and control. So this is also kind of like something I want to touch on as we go ahead. So this talk, as I've structured it, it's a very introductory talk. I'm going to mainly be dealing with kind of like hello world, but using that to dig deeper into certain concepts. So it should be beginner friendly, but I'm also aiming to reach out to intermediate developers, people who may have started developing, but for whatever reason, you may have started at a workplace, you only do Visual Studio, you only do you work with a system that where the build system is already developed for you. Maybe you just play around with the C++ syntax or whatever language, and kind of like give like a way to dig deeper into how the system works, especially the command line foundation. And also for experts, because I'm trying to find a way, like a roadmap of making sure that as much as we get really good at managing our templates and meta programming and like the really complex topics, that we don't leave the rest of the world behind. Like how do we kind of like bridge the gap to new learners? How do we kind of like keep the language alive? Because if it becomes too complicated, if we're dealing with really niche cases and like very, very specific performance areas, we could be bypassed by the rest of the world. So I was approaching this kind of like using an analogy to a movie. Like if you say for whatever reason walk into a theater 10 minutes late, and movies already begun and you kind of like missed some key plot points. Yes, you could, kind of like carry the movie along, but, at the end of the day, there's something that you're missing. There could be some joke that, the rest of the people are understanding because of something that was established in the first 2 minutes of the movie. And, you kind of like keep on missing the joke. So this picture is a picture of, I think one of the older machines. I don't know. For those who in there know, it could be a PDP-11 or something like that. One of the really, like, this is what computers looked like way back in the 70s and 80s. And the two gentlemen in the picture are Ken Thompson and Dennis Ritchie, who both worked at Bell Labs. And one of them is credited with the development of the Unix operating system, and the other with the development of the C programming language. And I mean, for those who do know like this history, how that, even Biani, who is the founder of C++, also was working with these people. So you can kind of like see the harmony, how they work together. And their work together is actually even evident today in how the C language and the Unix and Unix-based operating system like Linux, Mac OS, and what have you, are very, very tightly integrated. Like the foundation, it's a foundation of like, what we use, especially like say like in the internet, what is in the back end, the web servers, which are mostly Unix based. C and Unix are very essential to that history. So I look at this picture and see how, not only are they working together, their work actually shows even up to this day. It's something that, you should all kind of like emulate in whatever teams we have, that whatever work you do should really, kind of like stand the test of time. So I wanted to start by talking about the starting experience, like how do you get started developing C++? And it's my opinion that the starting experience can be a bit complicated, a bit confusing. It's not as simple as we would want it to be. So I'll kind of like just go over how to kind of like get started briefly, to like, just in case you're watching this and you want to learn C++, and to kind of like give like a guide of where to get started, especially how to get started with the command line. So with Windows, you generally have to use the Visual Studio build tools. And let me just switch over. Generally, if you search for how to install Visual Studio, it should take you to this site. And the default way to install, usually perhaps you'll install the Community Edition, which is free, which is a full version of Visual Studio, which will give you like the full experience. But if you're in a kind of like resource constrained scenario, and you only want to use the command line, there are the build tools for Visual Studio, which once you download those, they empower you to have just a command line interface into the Visual Studio. It's kind of like there's a special command line terminal which comes with Visual Studio, which is installed in the system, and that's how you'll get to program. But if you have the full Visual Studio experience, it is also possible, like the terminal, the special terminals, they give you an access to Visual Studio, but only using the command line. Just as an aside, that these days Windows allows for remote access via SSH. You can kind of like research how to get that started. But it's something that I find can empower you to, kind of like use the Windows computer in, kind of like a Unix-like way, where one computer, if you have many user accounts, can be used by more than one person to log in. And if you're only using the terminal environment, you can share the computer just like you would traditionally with a Unix system. Generally with Windows, you do get to, it's one person, one user, or even if they're shared users, you can only be one person at a time because of the nature of the graphical environment. This is one of the areas where using something like Visual Studio Code falls short, because every single person must have the machine, or if it's only one machine that you're sharing, then each person kind of like has to have their own time slot, which can be a little bit limiting depending on your situation. So I also want to mention that the terminal in Windows and Microsoft, I mean, just Windows in general, is a bit different from the Unix-based way of doing things. We have two approaches to it, one which is older than the other. One is, it's called, there's a program called CMD. If you just press the Windows key and run CMD, you'll get a terminal, but that's a much older terminal, which is based on DOS. And, based on the history of how we got here, DOS and Windows, they're not, they were inspired by Unix, but they were after a different goal. And the goal of DOS initially was just an operating system for use on personal computers. So they didn't come with a full suite of what the Unix-based systems offered, because at the time, Unix was used, kind of like, it's like one big computer, like a mainframe somewhere in, say, big institutions like a university, businesses, and what have you. And there would be terminals to connect to the main frame. But DOS, the approach for DOS was, it's a disk operating system. It was just a system for operating a single computer. And Windows eventually did grow from that. So the PowerShell is a newer shell, but it's based on some of the Microsoft technologies like .NET, where the Unix terminals are purely text-based. Like they work just text. Everything is text generally, except for binary files, but I'll get to that later. But in .NET, though you type commands that are in text, that is the underlying things that you're manipulating are not just text streams, but they are .NET objects, which is a bit different, but it does have an API that maps kind of like that, emulates the Unix way of doing things. I just wanted to mention that before we go ahead. So on macOS, I don't personally use macOS much, but I believe that just Xcode does have a workload for C++. So once you do that, you get access to I think the Clang toolset and the libc++. Then Linux, which I primarily use. It's for those who don't know, Linux is Unix based. It is inherited from Unix, but it behaves similarly to Unix, but isn't Unix. But generally, getting access to C++ and the compilers and what have you is generally straightforward. They're usually installed, or if they're not installed, whatever distribution you have, it's just a command away, and you should be able to have any terminal generally will have access to the compilers. So why the command line? What's so important about it? like I mentioned earlier, text is a foundational interface to the heart of our computers. We code in text. We access our programs through text. Even though, I mean, even the graphical interfaces mask the text-based nature of the program, because how things are stored on disk it's described using text paths. Where your programs are stored is text. Where files are stored, that is the primary interface for locating things on the operating system. Even if the graphical interfaces, kind of like hide that and give us fancy boxes and, this is a folder, this is a file. Underlying that is text. And so when we program, that's why we write everything in text and pass that to the compiler, which takes texts and converts that to binary, the binary language. I did talk about, I briefly mentioned access, like the ability to, use SSH to get to different places. It's a lot easier to transport text. In fact, even the internet, the HTTP protocol, which is the foundation of the internet as we know it, is largely text. Text is sent over, then to tell the browser what to do. So the same access that is available to us, I mean, through like the browser, it's with a terminal. I mean, to be able to access a terminal, just being able to get an SSH session to any computer anywhere increases access quite a lot. And so on the matter of learning, learning is done, kind of, you need like a playground. You need a place where you're exposed to whatever it is that you're learning. Even say, we're talking about programming language in this case, but even if you talk about natural language, say if I want to learn German, the best way I would do it is to, kind of like go to a place where German is spoken and see how it's spoken. And after some time, I'll kind of like pick it up. Same thing with how children learn language. So access, the ability to have access to compilers by more people will mean more people knowing how to code, and not just knowing how to code, but we need to raise up the standard of code, meaning that people have to have more access to better code practices, better, I mean, it comes through access and seeing it being done. And for that to happen, I mean, there has to be more access. And that's what one of the reasons I'm looking at the command line as a platform for that. And this is, very closely related to cost, because text does cost a lot less than graphical interfaces. And not only does it cost less, but just like I gave with the when I was talking about the Windows operating system, it gives a possibility to multiply a single system and make more people be able to use even a single system, because it's cost less to deal with text. And another very delicate issue when it comes to this is power, because one of the things that kind of like hinders access to computing is lack of power. Because places where, okay, fine, they may be able to buy a cheap computer, throwaway computer, but to power that computer is a whole other ball game, because it's usually a cheaper computer is usually older, uses more power, or doesn't have a battery backup at all. So even if you're to get power to those places, power in certain places outside of the cities and what have you can be really expensive. So this is like in relation to like laptops. How long will your laptop last when you're running the big heavy IDE that's doing all manner of things all day long, versus just having a very lightweight computer with just a terminal. So having that access at a lower cost is basically the key, I believe, to getting more exposure to computing and programming. And the other thing is power. That, like there may be this notion that the graphical way of doing things is more powerful. And yes, in some cases it can be. I mean, if you're doing art, it's definitely a lot easier to see what you're doing. But programming is just, it's text based. That's its primary thing. So I believe that, okay, this is something that could be subject to argument and discussion, but I do believe that if one does get better with the terminal, then it'll be easier and faster to, I mean, you may be better even if you use the other tools, but you'll have a skill set that, kind of like is not limited to a certain set of programs and what have you. So this is the reason why I think IDEs are good, but they're good as an after thing, that you should be starting with the command line, get good at that. Then you'll kind of like know what the IDE is doing for you. If the first exposure you have to C++ is an IDE with all manner of windows and doing debugging and analysis, it's too much. It's too much of a sensory overload. It's actually something I went through as I was learning, and the tools would overwhelm me. It was just too much. So I believe I did touch a bit on why C++. So I'll just move on to talking about a bit more about the command line. So as I mentioned earlier, that I talked about Unix, which is one of the, shall I say, founding operating systems. And there is this notion of programs starting other programs. Like Unix is a program, and it has other programs. Like there's a program that's when you boot up your system, there's the initial program that runs, and that program runs other programs and the like, that, which, I mean, that includes like the kernel, the Linux kernel, for example, or the NT kernel for Windows. Mac OS also has a Unix-based kernel. But so that concept of a program starting up other programs and managing them, and making sure that they stop and what have you, that's what the operating system is about. But at its heart, it's just another program. It's just a specialized program, and in fact, it's a program that's so powerful that we generally try to limit access to it. It's something that, I mean, shouldn't just be controlled by anybody. So there is a notion of the terminal, which is a mode of access. I mentioned briefly earlier that Unix was and is a multi-user system at its heart, where, because before, a computer was so expensive that it had to be shared by a number of people, and the access to the very expensive computer was through something called a terminal, which at its heart was a keyboard and a printer. And this would be connected to, like, there would be multiple of these connected to that one mainframe computer. And this was where we started. And if you look at where things graduated to next, the printer changed to a screen. And I know if you look at even your computer right now, you can kind of like see the same, kind of like shape, keyboard and a screen. But that kind of like fell behind as time went on, especially with the advent of the graphical interfaces and Windows and X11 and what have you. And what happened to the old terminal, the way of logging into our systems, was that it became just a single program. So it's just a window that would be open, and that would now emulate the old terminal. That's why we call it the terminal. But that is just the hardware. That's just what we type onto and what we see output from. But The core of what makes a terminal is a program called a shell, or in other words, it's also called the command line interpreter. And this is a program that takes what we type and also kind of like feeds us back what has been output by the program. And when we type, what we do, it's essentially a stream of characters, just with one key after the other. So that's how this has been the primary interface to the kernel of the computer for quite a while. That the commands you type, and then that brings also the notion of users who have access to the sensitive parts and other users who are just regular users. There's the matter of constraining who has access to the sensitive bit of the computer, which is the kernel. So the shell, if you think of the shell on say like a snail, the shell protects what is on the inside. That's kind of like what this program is about. And this is something that is at the foundation of what we have even now. So generally with the shell, it takes in commands, gives like an output, and waits for you to type in another command. And that can go on and on and on. And so this is how we find our programs. This is how we tell the computer, okay, fine, run me this program. And usually the operating system will go and look for that program and load it into memory. A program is generally a file, but this file is it contains the instructions that are needed for the computer to run generally. But with Unix, there's a bit more nuance to it, because they're programs that are not programs. They're kind of like the names of other programs kind of like joined together in a special way, to, kind of like creating a sequence of programs, like run this, then run this, then run this, and run this other one. And yeah, so there's that distinction. And that is something that actually, even up to today, is the foundation of virtually every system. Yeah, so I'm going to go briefly. I think I've mentioned this as we've been coming along, that there are the Unix-based shells, which are just text-based. Then there's a DOS, which I mentioned is something that came up with the DOS disk operating system. Things like PowerShell, which I've kind of like touched on. So one of the things about the shell is how to find out what you need to do, like the graphical environment. Like if you move your mouse to an icon, sometimes you get like a hint, like what that button does. But with on the command line, there is kind of like a standardized way of asking for help, which generally is like a dash and a H, or a dash and help. But different programs are different. Sometimes, I mean, if you type in a program, it'll kind of like tell you how it's to be used if maybe you use it the wrong way. And there's also this notion of arguments that I mentioned, that when you type in the terminal, say the name of a program, say I do ls, that program doesn't need any arguments. But if I do something like cat welcome.text, what the string welcome.text is a file name which I'm passing to the program called cat. So this is an argument to the program. So this is kind of like how we communicate with the terminal. Usually the first word is the name of a program. Then everything that follows after that is arguments to that program. So That's kind of like a just a brief overview of how the terminal works, and I'll just touch briefly about text, explain a little bit about what text is. Text is basically assigning, say, numbers to characters. That's kind of like how I'll just hand wave explain that. But it has been the foundation of how like the Unix system was built, how it would communicate with the server. And as things came along, before the Unix system came up, there used to be like the telegrams. The Unix system is actually inspired by something much older, which is like the telegram, and there had to be a code of passing the message over the wire. Like how do you, if a certain sequence of numbers comes, that's an A. If a certain sequence of numbers comes across the wire, that's a B. So that's how text would be passed along, and that's how the terminal would pass commands all the way to the computer. So there's the ASCII, which is kind of like the foundational text standard, which used to be 7 bits wide. And these 7 bits, the traditional 7 bits are still in use today. But the 7 bits are bit limited. They're not able to capture other languages beyond the English set of languages. And that brought us to Unicode, which kind of like assigns more bits to each character. But that's just something that I just wanted to mention. In fact, say something like the Windows user interface as we know it does use 16 bits for characters, but we can actually go even all the way up to 32 bits, and it can get quite complicated. I would recommend there's a talk by James McNellis on Unicode. I could search for that. It should be available on YouTube. So C++ is a programming language, and when we program in C++, we write files in text and pass those files as arguments to a compiler so that it can convert that to the machine code, which we can now call from the command line, and that's how we get to run our programs. And in fact, one of the smallest data type accepted in C and C++ is the character, which is an 8-bit value, with the 7 bits being capturing the traditional ASCII, and that's the last bit is can be used in different ways, which is kind of like related to Unicode, but that's another topic. So a program generally is just ones and zeros in a certain way, instructions that the operating system can pass to the hardware and obtain a result. So C++ and C and other languages like that are compiled languages that we have to first compile everything to the machine code and then pass the file that is converted to be able to run the program. But there also exist other types of programs like Python and JavaScript and what have you that primarily they're called translated languages because they're not converted all at a go, but they're kind of like converted bit by bit to tell them the computer what to do, and this can sometimes make them be a bit slow. I know that there are ways to precompile them, but just the primary way of accessing these languages is usually by translating them just bit by bit. So now on to command line C++ in particular. So I mentioned that the compiler it's a program which you invoke from the command line that reads these text files that we write in the language of C++ and outputs programs. And an important thing about that is text files are usually just sequence of characters from beginning to end, and the compiler expects the files to be in a certain format, which is defined by the language. And if you get something wrong, then the compiler will tell you where it found something wrong, and it'll report back and say, I found an error here, certain line, certain area of the text file, so that you can get to go and look at that text file and figure out what went wrong. So the compiler is a command line program. And just as I mentioned before, there's ways to get help and figure out, kind of like how it works. But there are so many options. But as a starting point, you can just do, or say on GCC and Clang on the Unix-based systems. G++ is compiler for Linux. Clang tends to be found on Apple and other Unix systems, but the point is they can be in both systems, but they follow the same convention. Microsoft, on the other hand, I mentioned that DOS was a different kind of shell or a different kind of interface. So its syntax is slightly different, but the concept is the same. Name of the program and an argument. And the argument for getting help is a slash and a question mark on MSVC. So today we'll just deal, simple Hello World programs. So this is just a simple text. This is a function called main that calls something called stdc out with a string of characters, hello world. And we can now compile the program. And just as a guide, like what is at the bottom there with the $sign, that's symbolic of a prompt. So C++ is shortcut for whatever C++ compiler, and the name of the file, which we called hello world.cpp. And I intentionally left out something just to show how the compiler communicates back with us. And the reason why I'm going to all of this, I know this may be kind of like simple things, is to illustrate the text, how text is the communication platform. We give the compiler text in the form of a file. It gives us text as in case anything goes wrong, explaining that, okay, in this file, in this function, there's something like it cannot understand. And it also gives like a hint. All that is in text. And why I'm bringing that up is that when you're using whatever IDE that, whatever you've come across, the IDE doesn't do anything much but interpret. It runs the compiler, which is a text program, but it reads what the compiler gives back, then kind of like communicates to you in a fancy way. So if you didn't have access to the IDEs and what have you, at the heart of it, all you need is the compiler. If you're able to now figure out that, to understand how it speaks. And that's a skill that I'm trying to emphasize, that it's important to know how to work without the IDEs doing all manner of fancy things for you, and just get down to the bare metal and see that, okay, fine, I got something wrong, certain file, a certain place, and what have you. So this is the corrected program. I was missing an include directive. And when I compile without, and just giving the name of the source file, I get a standard name, because I didn't tell the compiler what I would want my program to be called. There's usually a default name with GCC, that's a.out. And the same thing happens with Windows and DOS. So the cl.exe just takes the name of the file but its convention is slightly different. It doesn't do a.out because the way DOS works, the files usually need an extension. Unix doesn't have that limitation. So what DOS and the MSVC compiler will do will take the name of the source file and give you an output related to the source file that you give in this case, helloworld.exe. So I wanted to talk a bit about what happens when you run the compiler program. And in C++, there generally are these 4 stages of what happens. And the compiler allows us to control, a bit about this process, and in particular, where to stop. And that can give us like a kind of like interesting perspective on kind of like what is happening. And it's something that, from time to time, as you go on learning, it's good to kind of like play with the flags and see what's going on. So the first step when we're compiling our programs is the pre-processing. And by convention, this is something that the two different types of compile, the Unix and the DOS-based compilers do similarly. Is there's if you pass a flag of -e or \e, it tells the compiler to like stop, only pre-process and stop there. And if you do that, it'll show what it did in pre-processing. And I mean, in the program above, there was, I mentioned the #include iostream. Anything that starts with a hash, the hash include it's an instruction to the preprocessor. And what it means is find me this file and copy everything in it. It's, kind of like replace the string #include iostream or whatever header it is, and copy all that text and create one file out of that. So we can also, there are ways to save that to a file. So you can actually get like, oh, what does my source code file look like after the preprocessing stage. After that, or the next step, we can stop the whole process at the assembly stage, where the compiler stops at the stage where it has converted, it has read through the program, the whole program, including what has been preprocessed, and creates a representation of what kind of like it looked like on the machine, but kind of like in a human readable form. So those are some flags of how to do it. The first line is for the Unix based, and the other one for the MSVC based. And this can produce a file. And this if you've used the Compiler Explorer, this is kind of like what you usually have on the side window there. But it's something that you can do by yourself. Like you don't have to wait and do this on the internet. So from there, there's also the compilation phase. And what does the output of the compilation phase is an object file, which is actually in machine code. This if you try to read this, it's just gibberish, but it coincides with the assembly file. So the object files, which are actually in completely translated form, are passed on to something called a linker, which in actual sense is another program which is invoked by the compiler if you don't kind of like tamper with the flags. And this is what produces the program that we run. So I'll talk about libraries very briefly and explain that in terms of the file that we get when we do the compilation on with the compiler. The object file, it's possible to have more than one source file. And when we compile the many source files, they create many object files. One source file matches one object file. And a source file generally, you see, it contains all of the C++ things, all of the constructs, the numbers, functions, templates, and many other things, which we'll not get into now. But that's what is stored in an object file. And for a program to be able to run, it has to have all of its components together, which is what is done by the linker, which has a way of looking at, it understands, say, the object file and its structure and knows how to put it together. And there can be some errors that can come because of this. If, for example, you define a function twice with the same name and the same parameters and what have you. So there is a notion of headers, which mentioned the IOStream header, and we can also put part of our programs in headers. This is something that helps us to share the code. And headers, as you saw, it's something that is it is used to pass code, but in a not compiled way. So if I get somebody's library, a library generally consists of a header, which is uncompiled, and an object file, which is compiled. And the headers generally contain, definitions of, not definitions, but declarations, which is a bit of the jargon. But a declaration is, kind of like giving something a name, just stating that something like this exists. But when you're linking, look for something with this name. But that thing in itself is in the object file. So there's a bit of an example here where I factor out the greeting and put it in a separate file called libgreet. And it's going to be a function. And if I try to compile that file by itself, I get an error which comes from the linker. As you can see from LD. LD is the name of the program that actually does the linking. Even if the program that I ran was a compiler, I mentioned that the compiler does invoke the linker. So I'm mentioning this because these are the kind of errors you'll come across, but it's important to kind of like identify where the error is coming from. So in this case, this is coming from the linker, telling me that, it's not able to create a function because the convention is there must be a single main function for a program to be called complete. So this is just, if we only compile to an object file with a /c flag, I'd get an object file, but it not be a runnable program. And that's something that could be used as a library artifact. So just to correct that error, in this case, I've invoked the compiler, but with the two files, one that has a main, one that has the libgreet. And the purpose of this is to just to demonstrate that if you give the compiler everything it needs, then it will figure out how to link it all together, and the linker will not complain. But I did leave something out, which is the header file, and this is what the header file is for. The header file helps us to join the two things together. In this case, this is what a declaration looks like. There's a function, the function called greet, but it doesn't have a body. And this is included both in the place where I create the library file, and also the main file. So that the main file can kind of like create an object that says, okay, I'm calling something called greet, but I don't know where it is. The libgreet says I have created something called greet, but I don't know who will call me. So that's kind of like how we get to share code, and it's actually the foundation of how we get to interact with many people's code and many people's system and what have you. And in fact, the standard library uses the same principle. That when we included IOStream before, we didn't tell it anything about where IOStream is, but the IOStream header contains this thing called this std cout thing, whatever that is. Somewhere it has been compile to an object file. But that's usually known by the compiler. That's something that is hidden. It's not obvious. It's something that exists. It's also possible to do this with external libraries. This is, I'm using the format library to do to format the output. And I mean, this time around, if you try to run it, you get a linker error because I'm trying to use an external library. And the way to communicate to the compiler, and in actual sense, the linker, what to do when it, I mean, how to find the object files that it needs is with this -l FMT, which is by convention will search in places in the system and look for a library file called FMT and use that to link to the program that we are doing. That usually assumes that it's kind of like installed somewhere on the system. So in actual sense, in real world programming, I mean, we deal with a lot of source files and a lot of libraries, some ours, some not ours, and managing that in this simplistic way is a bit difficult. It's kind of like why I mentioned that, yes, the IDEs can help us in managing more complicated environments, and what they use behind the scenes are other programs called build systems, which have a way of describing where the headers are and where the sources are and which files to compile before which files and what have you. But they tend to be system specific. There's some that are, shall I say, portable, like Ninja. But historically, things like make files are mostly Unix, and there's a program called MS Build on the Windows platform, which is actually the heart of what the Visual Studio is about. When you create a project, when you create a solution and what have you, it's usually described in the MS Build language, so to speak. There's usually an MS Build file somewhere that describes how to put the files together and how to compile them together and what have you. But now this is now we can now get into system-specific scenarios. And so a lot of the time when we are working, this is what our IDEs are working with. But C++ being, shall I say, like a standardized language, is available on many platforms. And in order to be able to reach those platforms, we rely on a program like CMake, which helps us to build, to describe our programs and the files and what have you that we need in such a way that it can be used by other build systems in a way that they understand. And so I'll just give a brief overview of using CMake. Here's an example CMake file, and the essence of it is we describe, we tell it, I mean, that okay, we give it we give the version number of CMake, which is just a technicality, and we put this in a file called CMake list.txt. So if you kind of like go along with this, the files that we've been playing around with, and you put this CMake file, this now creates a way to create build systems out of the programs that we do. I mean, out of the sources that we have. So we usually say I want an executable, which is like a CMake function. If you want a program that can run, or you can tell it that I want a library, which is, it cannot run, but it finds a way to put the object files in a format that can be used by other programs. So once you kind of like described your program in a CMake kind of way, like I said, it's a recipe for building the build system. You kind of like tell it where you'd like to build your files. Like what we're doing before, we're doing everything in the same directory. But when you're working with something like CMake, there's a way to organize the files where you kind of like specify that I would like to build everything here in order to keep where you wrote your source codes clean. And we do that with this last line here, cmake-b. It's just another terminal program, though the IDEs have ways to kind of like do some of these things for you. So we specify the build directory and we tell it which build system that you'd like to use. You could say, I want to Visual Studio and stuff like that, and it will build for you something that can actually be opened even on Visual Studio. And then after that, we can just give a single command to build the program. But you can also use the build systems, which are actually other programs, say MS Build and what have you. If you use MS Build in the build directory, it knows what to do, because it's a language of describing what needs to be done, kind of like a recipe. So the purpose of this was mostly to kind of like just go behind the scenes of what happens with our tools. That the core point is that, they're just text-based tools, and if you, for whatever reason, don't have access to the IDE, or you choose not to use the IDE because you want to kind of like access your system in an unconventional way, you want to share out a single computer to more than one person. I envision a scenario where, just with a mobile phone, there are ways to have a terminal on a mobile phone that if you have a number of users, even if it's on a Windows machine, you can have that one computer being shared by a number of people on their mobile phones, and have each person having access to just the basic tooling for playing with C++ and what have you. So that's basically the gist of the talk, the command line C++. It's just giving an idea of how we can, kind of like get away from what I'll describe it like, the IDEs are kind of like glasses, like a mask of some kind, which can work in some cases. I mean, like sunglasses can help us on a bright sunny day, but in the middle of the night, they may not be so useful. So the idea is taking the time to kind of like play with the compiler itself. So just briefly, I just wanted to mention that, how does this relate to the Compiler Explorer? The Compiler Explorer, as many of you know, is a site where you can get to play with the compiler. But so what it does is, on the left here, we have, you see, a text editor. And this is where you can type whatever program, give it like a main function and what have you. And on the other side, you get the same output as you would have gotten with the compiler and the /s. And up in the window here, there's a place for compiler options, where you can kind of like, depending on the compiler that you've chosen, you can also choose different compilers and pass the same kind of flags that you'd pass on the command line, but this is like a web service. So I've seen, sometimes there have been attempts to teach C++, and people may use Compiler Explorer, but there's no direct correlation to like how does this relate to the command line. So at the heart of it, this website, there's a terminal somewhere that whatever you type here is passed onto a terminal somewhere. So if for whatever reason you don't have access to the internet, you can still play around as long as you understand text files, programs, program arguments, and the like. So that's basically what I wanted to get out of that, of this talk. There are a few resources that one can look into just to learn, or like once you have access now to a compiler and like a system where you can just compile and link and what have you. There are a few resources that I would recommend that you can kind of like take a look at. There are a few, there are a few resources out there for learning. I'll mention that the C++ Weekly channel by Jason Turner. he did do this a playlist for videos for learning. There are excellent videos by Mike Shah and many others. You kind of like pick what you want. But even if you don't have access to that, even just going onto CPP reference, you can kind of like play around with the examples here and there. And I'd also mention like looking into like deeper into the documentation for CMake to see, to kind of like explain further how these build systems are generated, and also the build systems themselves. If you search for them, for whatever build system in the platform that you have access to, it's good to know what is happening behind the scenes. And I believe that this would help us to work a lot better with whatever IDEs and what have you that we have access to. So I believe that's my talk. Yeah. Thank you very much for listening, and thank you for your time.
Thank you for speaking, Matthew. That was a really interesting introduction into command lines. And we're going to be following up with the next talk in a minute. So thank you for watching, and thank you for giving your talk, Matthew.
Thank you very much.